Welcome to this video. Today you are going to be learning a little bit more about work. Then I'm going to give you some notes on power. And then you will be doing some practice. Some practice on power. If we finish all of the practice, which we probably will, we will start a little bit on energy. And energy is a big one. We'll see there's all these different kinds or ways that energy can be stored, and different ways to calculate the amount of energy based on the storage form the energy has taken. So let's get to it. We're going to finish up just a couple of notes on work. Okay, the first thing we remember, work we defined as the magnitude of force times the magnitude of displacement times the cosine of the angle between them. And we simplified the equation. We don't actually write it this way that I just put onto the page. Instead, we say, okay, look, whenever we have really simple displacements, for example, you go 4 meters to the left. If your displacement is that simple and straightforward, 4 meters to the left, then delta r is negative 4 meters, and the absolute value of your displacement is just positive 4 meters, which also equals the distance you've traveled. So we come and we take this equation for work, and instead of putting delta r, absolute value of delta r, we put what it equals, distance, for simple cases. So we write that as distance. And what we do is we say, okay, look, it's kind of a pain to write the absolute value across or around the work. So instead of writing the absolute value, we just write F. And we all remember, whenever we write this equation for work, we all just have to remember that the F stands for the magnitude of the force. So we take away the direction in the equation for work. And cosine theta is the last thing, and as a reminder, sometimes we can write theta FD to remind ourselves that the angle theta is the angle between the force arrow and the displacement arrow, or the distance arrow if you want to call it that. So there's our equation for work, and I have a question based on what we just discussed. Is work a scalar or a vector? Which one do you think it is? Take a moment. Go ahead and answer this question in your notes. Everyone write down their answer, and then I'll call on someone. Okay. So, if we haven't all had a chance to think about this, go ahead and pause the video, and then unpause once you're ready to see. Okay, let's hear an answer from, who should we call on? Katie, what do you think is the answer? No, just kidding. I can't call on anyone. I'm not there to hear the answer. But I'm sure the answer would have been given correctly. Here's the answer. Work is the suspense, a scalar. It's a scalar because nothing that we multiply has direction. In the equation for work, F doesn't have direction, D doesn't have direction, and of course, cosine of theta doesn't have direction. And therefore, there's nothing to give direction to the work itself. Okay? So it's a scalar. Nothing. So why is it a scalar? Why is it a scalar? That's what I'm answering in the next bullet. Why? And the answer is because nothing that we multiply has direction. There is nowhere for the direction to come from. In other words, what would the direction be? If this doesn't have direction and that, if none have direction, then work There's nowhere for the work to get its direction. Okay, I think that's sufficiently clear. Here's the thing though. We already said work can be negative. Work can be negative, right? For example, if we have a block and we have a bunch of forces acting on it so that the block travels rightward, if a force like kinetic friction is pulling in the opposite direction as the distance traveled, or as the displacement, that's when you have negative work. The kinetic friction force does negative work. If you had like a pulling force up like that, its parallel component would look like this. That's the component parallel to distance. Here's the component perpendicular. And because the parallel component, this green line right here, it also points in the opposite direction as distance. And so that means that this pulling force will do negative work as well. Whenever the force is in the opposite direction as the distance, there's negative work being done by that force. So the negative sign clearly does not make it a vector. The negative sign doesn't indicate direction. It doesn't indicate a direction of the work. And that is just the same as with temperature. If you have a temperature of negative 70 degrees, or let's say negative 10 degrees Fahrenheit, the negative sign doesn't mean to the left or to the right or up or down. It's just part of the magnitude. Okay, we are now on to power. Power, right? So power is a very similar idea, a very similar concept to work. We define power. Power is, it's a rate in time. It's the rate at which work is done or energy is transformed / supplied. Transformed or supplied. Can we read this? The equation for power is defined as the work done over time, or as the energy. We should probably say delta E. We're going to learn more about energy. We haven't learned about it yet. But it's the amount of energy transformed, the change in energy, or the amount of energy supplied, the amount put into a system over the time it took for that energy to be put into the system. So there's our equation. Power, because work is a scalar, because time is a scalar, power also is a scalar. And you probably can guess energy will also be a scalar. Power is a scalar, and what else do we know about power? The unit for power is, what do you think is the unit for power? What is the unit of power? Anyone know? What is it? What is the answer? The watt. Ha 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 ha. Okay, yes, hilarious. Let's take that out. Maybe not so much. The unit of power is the watt. 1 watt. You can look at the equation for power and figure out what the watt is equal to. You just, in the numerator here, we want to plug in the unit of work. The unit of work is the joule. In the denominator, we want to plug in the unit of time, which is the second. So 1 watt is equal to 1 joule per second. Now we have to be very, very careful. Here's what we have to be careful about. Power is measured in watts. Work is measured in joules. So you really want to make sure you don't get confused by the fact that there's 2 different W's here. One W stands for work, and the other W stands for the watt. But work is not measured. Work is not measured in watts. Work is measured in joules. Power is measured in watts. So this is just something to be careful of. When you write the W down, keep in mind it can mean 2 different things, and you alone have to be the one to recall what it means based on the context that you're using. Okay, so we have an equation for power. Let's see, maybe a different color. Let's use blue. Power is the work done over time. That's the equation we'll be using mostly in this unit. The one with energy, the other equation with energy, is something that we'll get to later in the year. And next year in IB Physics. So power is work over time. There are some good equations we can write down. Work, we know, is F d cosine theta Fd over time. So that's one equation. We can actually write it that way, or we can say power times the time is equal to Fd cosine theta. That's a d. And so that's one equation we can write down. Maybe we should box it. Another equation is this. Power equals, okay, it's the same thing again, right? Fd cosine theta between those F and D arrows. But if we think about this just for a moment, distance over time, that is something we already know. Distance over time is speed. So power is F times the speed. Let me see if I can do a better V. Times the cosine of theta. It's not Fd anymore because d is no longer in the equation. Instead, it's Fv. And here's why that's true. If you have an object and the object moves to the right some amount d, then that means, and let's say the force was applied like this, right? We could draw a very similar picture, but instead of drawing the d arrow, we could show the velocity arrow. If the object is moving to the right, then its velocity is to the right. So we can see just by inspecting the picture, we can see very clearly, theta Fd is really no different from theta Fv. So it's perfectly acceptable for us to replace theta Fd with theta Fv because those are in fact the same angle. My picture here proves that, or at least convinces me of it. And these are the equations. These are the equations for work that we'll be using. In addition to those, we will also have the good old equation at the top. Sometimes that's one that we'll use. And the next thing you're going to do is a little bit of practice using these equations. There's one small thing to point out. Power, like work, is the phrasing we used, developed or delivered by an individual force. In other words, if we have a block right here, and the block is moving some distance to the right, you could have like a first applied force right there, and you could have a second kinetic friction force right there. And in this example, the power developed by FA is different from the power developed by kinetic friction. We can inspect the power developed for different individual forces. F right here is an individual force. So just because you plug in an applied force and you calculate maybe a power value doesn't mean the power for kinetic friction will be the same, because when you inspect different forces, the value of power likely will change. So the final thing that I want to do is I want to show you the setup that we're going to be using for power problems. Power probs. Because many of these, oh my gosh, many of these, I cannot talk and write at the same time. Many of these will have a very similar setup. If the object is moving at constant velocity, okay? Let's imagine that maybe the object is on the ground and there's some machine pulling to the right, or maybe it's the engine, so maybe the block really actually represents a car, and the car has some engine which is sort of driving it forward, the thrust, you might say. We could call that the applied force. F sub A, the applied force. And then of course on a horizontal surface, which is so all we'll deal with, at least we might get to angles, inclines. So anyway, for now let's imagine horizontal surface. The force applied is to the right. If it's moving at constant velocity, then there has to be some other force to the left which balances the applied force. That's going to be kinetic friction. And what else? Let's just call it kinetic friction, why not? And then, if this is true, if there's constant velocity, we know that the applied force, which might be because of an engine or so forth, will be balancing the kinetic friction force. We know the normal force will be balancing mg. Okay? And that is all true because of the fact there's constant velocity. We know our force is balanced because of this principle, because of this fact. In most cases, we'll be given or asked to find the power by the applied force, Fa. And based on the equations that we saw, we'll have a couple of choices. We'll have Fa times d times cosine of the angle between Fa and d over the time. And if we look at the picture, we can very clearly see if the object is being pushed to the right and kinetic friction pulls the other way to the left, that means it has to be moving some distance d to the right on the horizontal surface. And that means if it's moving to the right in a really simple case like this, in such simple cases, theta will be 0 and the cosine of 0 is all 1. However, the kinetic friction force is equal to the applied force. So I can replace Fa with Fk, And Fk we know is mu k times the normal force. And mu times the normal force, I can change normal force to mg, and that gives me this. Power developed by the applied force. Okay. Don't memorize this equation. That's not acceptable. Instead, what you want to be able to do is use these two facts to replace Fa, and then later to replace Fn. Okay. Another kind of problem that we'll see, power probs, is one where we have a horizontal surface like this, but instead of moving at constant velocity, the object is accelerating at some value a. Maybe a is 10 meters per second, maybe it's 0.2 meters per second, who knows? Some value, some number of meters per second. If it's accelerating, then that means, and so we're going to take the simple case where there's an applied force to the right, and there's kinetic friction to the left, right? So, I should draw my kinetic friction arrow the same length as the applied force, right? Because it has constant velocity. Wait, no I shouldn't. It's accelerating. And it's accelerating to the right, the problem would say. So if it's accelerating, that means kinetic friction is smaller than the applied force. And gravity pulls down, normal force points up. Fn. If it's accelerating to the right, if the acceleration is rightward only, then that means there's no up acceleration. So Fn is not bigger than mg because it's not accelerating up. And there's no down acceleration because mg, there's no down acceleration because it's not, the block's not crushing the ground. It's not accelerating downward. If there's no downward acceleration, mg is just as big as Fn, which means we do still have balancing. Even when there's acceleration, we might have some balancing just of one direction. And on the other hand, Fa is bigger than Fk because we're accelerating to the right, but we don't need to show that. As before, kinetic friction is always equal to mu times the normal force, or in this case, mu times mg, since Fn is equal to mg. What you also will have to use in these equations, and again, I'm boxing these, but don't memorize them. It's important each time to sort of go through this thought process. And there may even be multiple choice questions, on the next test where I show you this picture and I say, the block is accelerating to the right. Which of the following is true? And you have to say Fn is equal to mg, then you also have to say Fa is bigger than Fk. So in addition to this equation that I just boxed, we also will have Newton's second law. The sum of the x forces is equal to the mass times the x direction acceleration. I'm going to call rightward positive and leftward negative, which means Fa is positive, Fk is negative, right? Fa is positive, Fk is negative. So positive Fa plus a negative Fk equals m times the x acceleration. But then Fk I can replace with mu mg. And that gives me this. So this is another equation you might be arriving at through your work. Again, like before, don't just memorize the boxed equations. These are things you want to be able to derive and use based on your problem solving. Okay, the last example is where we are moving a block up an incline. So let's say we have some angle theta, right? And there's an applied force like this. There's kinetic friction pulling back. There's gravity pulling down. Shoot, my gravity arrow is not very good. Gravity pulling down. Let me try it again. Make that straight. It's a little better. And then there's also a normal force pushing perpendicularly to the ramp. So the normal force is sort of down here. It goes up like that. I need to practice using my stylus more. We can break the normal force. We can break gravity into a component like this. mg cosine theta is that component because this angle also is the same as the ramp incline. The incline here is equal to that angle. And then there's a component like this, which is mg sine theta. And the two components are perpendicular to each other because the tilted x direction and the tilted y direction are at a right angle. So this is the x-axis component, this is the y-axis component. In a problem like this, if we have constant velocity, then the power being done, let's say by the applied force, for example, is going to be Fa times the distance times the cosine of the angle between them, which will be 0. There's the equation. The block, we're going to have it moving up some amount d. Whoops, it's going too far, isn't it? I should probably bring that arrow back so it's not running off of the ramp. Going up some amount d. Okay. And so the angle theta between the applied force, which is up the ramp, and the distance, which is up the ramp, that angle is 0 degrees. And because the angle is 0, the cosine of 0 is 1. And what do we get? Power is F applied times d over delta t. Now, in these problems, there will be problems where we have the block going. It'll tell us in the problem it's moving up at constant velocity. If that's true, then the rightward forces balance the leftward forces. So what are the forces that point right? I'm going to circle them in green. It's just the applied force, Fa. What are the forces that point left? It's the kinetic friction and mg sine theta. So mg sine theta plus kinetic friction. We can find what that equals. It's always mu times Fn. And of course the normal force balances with the tilted component, the tilted y component of gravity, mg cosine 30. So the friction is mu times mg cosine 30. And I can put that in mu times mg cosine theta, where theta is the ramp angle, right? This theta here. So you can use that equation in problems with power as well to find the applied force when given, if you're given m and mu and theta. You can find the applied force and find the power developed by the applied force as it moves the block some distance d over some period of time t.